Hello, this is Xuan from Johns Hopkins University. In this video, I will share with you a toolkit we created. To be specific, it's a hyperparameter optimization toolkit built for neural-machine translation research. I'll first motivate the work, then briefly explain some of our implementation decisions, and in the end, I will show a demo of our toolkit. Hyperparameters are important. This figure shows blue scores for more than 700 NMT models we have trained before. Those models vary only in hyperparameters. There is a large variance in blue, which motivates the importance of hyperparameter tuning. Hyperparameters are configurations of a model that are not updated in training. For example, in terms of a transformer, there are architecture hyperparameters such as number of layers and training pipeline hyperparameters such as number of subword units and optimizer hyperparameters such as learning rate. Hyperparameter optimization or automatic hyperparameter search might mean differently to different people. For developers and MT researchers, it reduces effort to obtain SOTA results. Let's first define the problem of hyperparameter optimization. In HPO, we're not too concerned with how model is trained. We won't dive into the model parameters. Instead, we just focus on the hyperparameters and how they would impact the model performance. Take deep learning models, for instance. We might want to tune hyperparameters like the number of layers, the number of units per layer, the optimization type, and the learning rate. Our goal is to find the best configurations for these hyperparameters with as few model evaluations as possible. We've all been through this in practice. We pick values for hyperparameters, train models with those settings, and then get evaluations. It could be accuracy, WER, or blue score. And after that, we adjust hyperparameters and train the model again, hoping for better evaluation results. To select hyperparameters, we often use default values or rely on heuristic rules. It's a very tiresome process and there's no guarantee it will pay off. So, is there a way to do better than this? Or can we avoid this tedious process of manual tuning? It turns out that we can actually replace ourselves or any wary graduate students with more reliable machines or algorithms in the loop. That happy, smart-looking robot in the picture saves us from the tedious work of manual tuning, or thanks to its HPL algorithm. HPL takes hyperparameters and evaluation results as input and suggests new hyperparameter configurations. The goal is to find the optimal hyperparameters with fewer searches. HPL methods typically require waiting for the model to converge. This waiting time can be a bottleneck for HPL runs. However, it turns out we don't always have to train to completion every time. Dodge 2020 demonstrated that performance early in training is highly correlated with performance later in training. As a result, we can apply multi-fidelity optimization, which uses more affordable approximations of models. For example, we could run fewer training steps before gathering performance results. Successive halving is a prime example of multi-fidelity optimization methods. The concept is pretty straightforward. It assumes that all configurations can be stopped early and aims to allocate most resources to the most promising configurations. Picture this: you have n different configurations and a certain budget, like training time. In each iteration, as shown in the figure, successive halving returns the top half of the configurations and discards the less effective half. This process continues until only one configuration remains, and the method wraps up when it reaches its maximum budget. And we call each column in this figure a run. Okay, and we'll use this term run in following. In terms of our toolkit, we implemented an asynchronous version of successive halving, or ASHA. In sequential successive halving, the algorithm waits for all configurations in a run to complete before promoting any of them to the next run. ASHA, on the other hand, removes this bottleneck by allowing asynchronous promotions. The idea here is to promote a configuration to the next run when there's an idle worker or when a configuration has already secured a position in the next run. And this approach ensures parallelization with optimal GPU utilization. For example, at this point of one ASHA running, we promote configuration 4 from run 0 to run 1, even though not all the jobs in run 0 are finished. Same for promoting configuration 8 from run 1 to run 2. This is asynchronous because we do not promote until all the jobs in run 1 are finished. HPO algorithms are generally straightforward to implement. The real challenge lies in interacting with HPO algorithms and the underlying computing infrastructure. When designing HPO software, one needs to consider their specific computing environment and how to automatically submit jobs, check job status, evaluate and collect the results, parallelize tasks, and maximize GPU utilization. At the same time, the software should be flexible enough to allow users to customize their HPO runs by specifying arguments such as the number of GPUs, the number of configurations to try, and the number of epochs for each run. It's not trivial to hesitate on the decision whether to use existing HPO toolkits or implement our own. So if you go for an existing HPO toolkit, you might have to rework your entire training pipeline. But if you already got a solid training pipeline like Amazon Sakai for machine transition, and you are not too keen on messing with it, you might consider creating an HPO wrapper instead. Take our HPO toolkit as an example. This second option is actually quite doable and is a perfect solution for our needs. Our HPO toolkit is created on top of Amazon Sakai. Amazon Sakai is an open-source sequence-to-sequence framework for MMT built on PyTorch. Kevin developed Sakai recipes, which consist of training scripts and recipes specifically designed for the Sakai toolkit. You can find the Sakai recipes with HPO support on GitHub. To be specific, we implemented an automatic hyperparameter search using asynchronous successive halving on top of Sakai recipes. In this video, I will show you how to use our hyperparameter optimization toolkit with a toy example. We start by cloning the Sakai recipes 3 Git repo and following the instructions here to set up the Anaconda environment and install the package. After doing that, let's first generate a hyperparameter search space. Let's name it space 3 and copy the configuration zip file under the new directory. In this zip file, we can set the values of hyperparameters we want to do. For example, for the transformer model size, we can try these 3 values. Next, we need to generate a bunch of configuration files based on the zip file. Each of them configures or specifies a model. We need to also generate BPs accordingly using this line of command. To save time, I have already generated them in advance. I'll just copy them here. The original search space might be too large, so we give users the freedom to choose whether to just do hyperparameter search on a subspace. For example, we say we want to try 10 configurations and we decide to save the intermediate results in round 1. Until now, we have finished all the preparing work. Let's go back to the AutoML directory. We can simply run this script to start the automatic hyperparameter tuning on the grid. Users are free to specify ASHA-related arguments and how many GPUs that can be allocated to the hyperparameter search. Let's run it. Nothing more we need to do from here. We can just relax or work on something else. This is an example of the log of a finished job. In the end, it reports the performance of models at different stages and shows which ones moved on and which ones got eliminated. In this example, the best model we got is model number 3, which achieves 10.6 blue score.